Okay, we are now moving on to consider a combination of two motions which produces what is known as projectile motion. If we have a look at this diagram here on the left, and just take note, this material does not have to go into your notes. There's a number of slides here which are really just by way of explanation. All right, so we drop an object and we can see from the positions as the object falls that is getting further and further apart. So in terms of this vertical motion of the object, we have acceleration, and we've talked about acceleration of free fall now in a period or two. Taking another motion, if we ignore the effects of any friction for this object moving along a horizontal surface, then the object would move it. The object moves with constant velocity. And that's indicated in the diagram up there by the fact that the spacings at equal time intervals, the distance traveled, if you like, in equal time intervals is the same. So what we're going to do for projectile motion is we're going to take these two previous motions, the motion of an object falling under the influence of gravity, free fall, and the motion of an object, oops, sorry, we jumped ahead there, one too many, and the motion of an object traveling horizontally. We're going to take those two motions as shown here, and we're going to superimpose those together. So if we have an object that would fall and reach that position there, if at the same time it travels horizontally that far, the object actually would end up there. So it's both moved to the right and accelerated downwards. This next object here, I'll use green for it, this one here, would have fallen further, but at the same time traveled further. So it would reach there. The next object, this one here, would have fallen further, but traveled an equal distance horizontally, and so on. And so we get the path of a projectile, and there it is illustrated there. And if we have a look at the vectors involved here, I think we can see that we've got velocity, equal velocity, equal velocity, equal velocity, equal velocity. So constant horizontal velocity, but at the same time, increasing velocity in that direction, represented by the fact, or it's falling greater distances, I should say, indicating that the object is accelerating. If we have a look at the motion of a projectile over a complete path, this previous diagram here, in a sense, really is dealing with half of the motion because we're projecting something horizontally. If we look at a more general scenario, we're projecting something at some initial angle like so. But again, if we study the motion, constant horizontal velocity right throughout the motion. The length of each of those vectors is the same. If we look at the vertical, getting less and less, and then starts getting more and more in the opposite direction as the object goes up and comes down. So that's our acceleration. Whether we're heading upwards, it's accelerating downwards, or if we're going downwards over here, we're accelerating downwards. It's the same situation, the same downwards acceleration at work in both scenarios. And that diagram there really just breaks it up into those two parts. Up here we're saying that the y components increase due to the force of gravity, and in this particular case, as we're heading upwards, the y components decrease due to the force of gravity. But in both cases, the x components of the motion remain constant. All right, so here's an example of a football being kicked. There are a number of possibilities in terms of the path of that football. It could be given the same velocity, but depends on the angle as to what actually happens. And it's interesting to note that if the football is fired at, say, 15 degrees, or fired at 75 degrees, which is the complementary angle, 90 minus 15, we end up in both cases getting the projectile actually traveling the same distance. In a similar manner, if the projectile is fired at the 30 degrees or at the 60 degrees, it ends up traveling the same distance. But the 45 degrees, which is that sort of angle in the middle, if you like, halfway up towards 90, is the one at which the projectile travels the greatest distance overall. Okay, there is a formula in your textbook, or a derivation of the formula in your textbook that would allow you to figure out that that maximum range would be produced at a 45-degree angle of projection. Of course, assuming no influence of air resistance. Here's a tennis ball bouncing. I think we can see from looking at this diagram, that if we sort of did the same sort of thing, equal time intervals, we would get equal distances traveled in the horizontal direction, while the vertical distances being traveled, get less here and get more down the other side. What's happening over here is that the ball has bounced, and then the ball has bounced again, each time losing energy in the process of bouncing. All right, we come to the part that I want you to actually write into your notes, and this is the part that's covered by the PDF. All right, so if an object is projected horizontally by giving it some initial velocity, so we fire it like shooting a bullet from a gun, something like that, it will follow a curved path. If there is no air resistance, we say no air resistance, or it could be in many cases that we say that air resistance is negligible, meaning it's small enough to not to worry about it. If there's no air resistance, then the only force acting on the object is the force due to gravity. Okay, and it's a force that produces a change in motion. So analysis of the motion of the object shows that its motion can be considered as two, and this is a key idea, two independent components at right angles to each other. If we say the motions are independent, it means we can do calculations quite separately about the two parts of the motion. All right, so in this situation, we have got, in the horizontal direction then, we have got uniform horizontal velocity. And when we're dealing with uniform velocity, there's only really one formula that has to be applied, and that is the formula that says that V equals d over t, or delta S over t. All right, that's not very well drawn. V equals, let's just write it as S. I know you could argue it's delta S over t. That's the only equation because there's no acceleration here. And then the second component is uniform downwards or vertical acceleration. So that's the one where G equals 9.8 meters per second squared, and that's where we apply the equations of motion. One other little point just in passing to note is that the path of a projectile is called its trajectory. You'll sometimes see mentioned on TV and so on, the discussion about the trajectory of perhaps a satellite that's falling back on the Earth or something like that.